Okay, so this is just going to be a quick introduction to how to approach question 3. Again, like the question says, there's nothing there, but I will try to make it easier and kind of less scary, even though like there genuinely is nothing there. So I'll first very quickly go over Hopfeld networks again. Sorry. So what do we want to do? So we want to try to store memories kind of in a metaphorical kind of way, a little bit, the way the brain does. So computers store memories by basically writing numbers to a table. The memory of a computer is a table. You can think of it as a list of integers. So anything that you remember is encoded as integers in a computer, if you remember it in a computer ordinarily, and it's just stored like that. But the brain works differently. So memories are somehow, we don't exactly know how, and Hopfield and Hinton kind of tried to work on that. They are stored somehow in terms of patterns of neurons firing. We don't know exactly how. So what are neurons? Well, they're cells in the brain. They fire electrical pulses at different frequencies. One neuron firing, we know, can cause another neuron to fire as well. So it's basically nerve cells that are connected between each other, and one starts firing, then maybe another starts firing. Because of that, there could be feedback loops, there can be lots of stuff. So Hopfield's idea is to try to show that you can do something with that kind of computation where, one nerve cell firing causes something to happen with another cell fire. So the key there is he showed that memories, meaning, memories of vectors of numbers really, can be stored and retrieved reasonably efficiently. So in this class, you've seen how they can be retrieved inefficiently when we were doing the for loop to try all the possible minima. And in this lab, you're going to show that, in a simplified kind of scenario, you can make them get stored reasonably efficiently. So here's the Hopfield network that we're talking about. Of course, it's, very small and not doing kind of all that much, like remembering triplets of numbers, but still, like, that is the Hopfield network. So it's slightly simplified because it removed stuff that we're not using, but basically that's it. So how does it work? So there are, the nodes x0, x1, x2. So those are kind of analogous to brain cells. And then there are the weights. So the weights indicate kind of how much is x0 connected to x1, for example. The answer is, well, the weight is 2. So, okay. So we have this notion of the energy function. Don't think about it as like energy in physics, although there is an analogy. Think about it as just a function. So what is the function? Well, if you write it with sigma notation, it looks like this. But if you just have 3 x's, you can write it out, right? So like I smaller than j just means that when you're writing this product, x something times x something, this index should be smaller than this index. That's all it is. So we only have, 3 tuples of 2 x's where xi is smaller than j, and this is x0, x1, x0, x2, and x1, x2. And then the product is like 2, so Sij is the weight between I and j. I'll change it to w. And then we're saying, okay, so this times the weight. So 2 times x0 times x1, and then x0 times x1, x0 times x2 times minus 1. So that's this one. And then x1 times x2 times 1. So that's this term. That's all it is. And then if we say that the x's could only be minus 1 and 1, which is one setting in which people do that, then memories would be triplets x0, x1, x2, where the energy, if you plug x0, x1, x2, is small. So if the weights are set to 2 minus 1, 1, then the memories are the minima or approximately the minima of this energy function. And we saw in class that there's 4 such minima for those particular weights. So how to compute it in Python? Well, you just need to compute this formula. So I just compute, the 3 terms, and I return minus the sum of the 3 terms. So term 1 rather, and then term 2, and then term 3. Here's a way to print out all the possible energies for all the possible triplets. So that's what we've done in class. So you say, for x0, and x0 could be -1, it could be 1. So this is just a list, right? x0 is -1 or 1. And then x1 is also -1 or 1, and so on. And then we just print out, x0, x1, x2, and then the energy that corresponds to x0, x1, x2, because we just computed it. We called the function e over here, and that computed it. So that's what it is. So now, this is a little bit different from what you said in lecture. So now we are setting the weights like this, and then we're saying print all energies, and that prints out the energies that correspond to every possible x. So x is the vector, x0, x1, x2. And you see that the minima are, this guy, and this guy, and this guy, and this guy. So now the goal in question 3 is to try to store new memories. So what I mean by that is I want to keep the old memories. So I want for the old memories to still be the same minima, but I also want the energy function to have a new minimum. And the way I want to do it is by changing the weights. So I want to change this W, this W, this W just a little bit so that the old minima are still kind of there, but there's also a new minimum. And the strategy is like this. I want to make E small when I plug in x equals x0, x1, x2 for a particular x0, x1, x2. Right? They have a memory x0, x1, x2 in mind, so like -1, 1, 1 in question 3. So how do I do that? Well, I want to make this guy as small as possible. So that means that I want to make the thing inside the parentheses as large as possible. So how do I increase it? Well, I can look at, okay, like what is x0, x1? If it's positive, then I just want to push W01 up a little bit. So that if I plug in the particular x0, x1, well, if I make W01 slightly larger, then x0, x1 would correspond to a smaller energy because I'm pushing this term up. And then if, for example, x0 times x2 is negative, then it's the other way. I want to push W02 down because I want to make this term as large as possible and this negative. Okay. So that's all it is. So I want to decide, do I want to push W01 up by 0.1 or down by 0.1? I want to decide if I want to push W02 up or down. And I want to decide the same for W12. So this is literally 3 if statements. So just in the main block, write those 3 if statements and adjust W01, W02, W12 by either 0.1 or negative 0.1. And then in part B, I'm asking you to do that and then to call print all energies again and to show the effect of having adjusted W01, W02, W12 by just a little bit. And then in part C, I'm saying, don't just do it once, do it several times. And what you'll see is that if you do it several times, but not too many times, and put it in a function, right? So just like a separate and new function. So what you'll see is that if you do that several times, obviously kind of you're pushing it so that x0, x1, x2, the particular one, is more and more looking like a new minimum. But at the same time, you'll see that if you do it too many times, well, the old memories might go away because you adjusted the weights too much. And also you might have created fake memories. So that's bad. So figure out, so about like 4 or 5 iterations is ideal. In this case, figure out how many iterations you need in order to keep the old memories, not create any new fake memories, but yes, create the old memory, the new memory that you actually want. That's it. So part B is literally just 3 if statements in the main block. And then part C is just take that, put it in a for loop and stick it in a function. That's it. Okay. All right. Enjoy the lab.